Thank you, Matt. Hi, everyone. It's me again. Up. Yeah. I'm Poyzan. Today, there will be Clive, Jason Nochlin, and Trevor Whitney. We all work for the Loki team. And in this session, we will walk you through the internals of our new architecture. So if you were in the keynote, you got a preview, and you have seen this slide probably earlier. But today, in this hour, we want to unpack what exactly we are changing, and more importantly, why are we changing? Let's do a quick look back. How did we end up here? So in good old days, we used to have plain text files on servers. We would SSH into the box, try to find a file, try to find the error line, and you kind of hope after a certain time you were in the right box. And then came phase 2. We started aggregating those logs in a dedicated server and graphing over the lines. Yeah, it made it simpler to search, but it was impossible to scale because it was limited by the size of the box. And then there came phase 2, dedicated, specialized logging services. This is where Loki entered the picture. And now we are already in phase 4, where structured logging is now the default. Like I said before, OpenTelemetry adoption is also accelerating it. Now we have meaningful key value pairs that either represent something about infrastructure or our business logic in it. But let's take a pause here. In phase 3, Loki changed the game. The core principle is we didn't have to index every line. And on top, we would select a subset of streams and then search within them. These design decisions made Loki incredibly easy to operate and cheaper to run compared to the alternatives. And it worked. The numbers show it, right? 30,000 stars nearly, over 400,000 deployments in the wild. Loki is the backbone of observability in a lot of organizations. But this success is bringing new demands. And questions like, how many failures did each user experience in this time period is a fundamentally different workload than what Loki is designed for. So that's why we are changing the fundamentals. So we group our current bottlenecks into 4, and each of us is going to walk you through one of these today. Loki has outgrown the initial trades-off of the write path design. 3 times replication and read-write coupling had a reason for it, but now they're becoming operational bottlenecks for us. And then, in order to answer queries with the new structured logging world, we have to read multiple dimensions from every log line. Dimension is a generic word here. We mean fields, key value pairs. But again, back to the question, how many users experienced a failure in this time period requires 2 answers, the responses and the users. But Loki has to parse the entire line, and we know up to 97% of the log message is not needed to answer this question. Loki is doing a lot of work to answer the question in the way it's designed, and we are also trying to reduce the work that it's doing at a time. And finally, looking for a specific log line with no direction to Loki, no stream selectors, is slow by definition, needle-in-the-haystack queries. So we are also going to visit new perspectives for this. So here's our 4 solutions. In a second, I'm going to walk you through the new write path. Ben and Trevor will tell you all about the Columnar format and the new query engine. And Jason will give us new perspectives on how we can solve the needle-in-the-haystack lookups. So let's do a mini deep dive. This is Loki today. Writes come in to the distributors. They get fan out to 3 zones. Ingesters will buffer logs in memory. They will compact them and flush to the object storage. And on the read side, front-end query, front-end shards query into smaller bits of work. And then it either queries them against the object storage or cache in between, or forwards the queries to ingesters to be executed. Notice that the ingester is sitting on both paths. So let's revisit why Loki is designed this way. To make it highly available, Loki chose to serve reads from memory. So they are immediately available the moment you send them. But in return, at the scale we operate now, a heavy query hits, and it will slow down writes and will result in 500s to the end user. Or a heavy query, again, can ingesters if it's asking too many streams at the same time. So moving on to the second one, making it durable, Loki decided to replicate data 3 times. And it aims to flush them at the same time using the timestamp. However, when the ingesters go out of sync, and if you remember, they have the tendency to do that quite frequently, it will result in duplicates in the object storage. And these duplicates have to be deduplicated at the query time. And the third one is a difficult one to reason around. So Loki currently distributors are distributing the streams by hash ID. This results in high throughput, chunky streams on the same ingester sometimes. And it creates imbalances in the same workload. We have mitigations around this, like auto stream tuning, but it's hard to tune even for highly skilled operators like ourselves in Grafana. So it's also hard to manage for us. Remember, these are not bad decisions for what Loki was designed for. It was optimized for write path. But pushing it to its scales, these trade-offs now compound. So the new write path. We introduced Kafka to our write path. Distributors are now writing to the durable stream layer, Kafka. And each partition is now consumed by an ingester. As writes are acknowledged before the ingesters, now we have the option to completely separate read and write path without actually compromising on high availability. And then Kafka allows us to replay data with an offstart, right? So data is processed once and exactly once. Without compromising on durability, we can now move the replication to Kafka, but remove them from ingesters. And finally, unlike a hash stream ID based hashing, Kafka gives us the option to partition bar volume. It gives us a lot of configurability around us, so it enables more uniform workloads among the ingesters. We have to be honest here. We resisted to any major dependencies for a long time. Loki's identity has always been its simplicity. And we are aware that adding Kafka is a big operational complexity. But the scale, as we push to petabytes, running existing Loki is not any easier comparatively. So reconsidering the design trade-offs that we just talked about, we believe this complexity is justified now. Let's recap. The new world on the new write pipeline gives us complete write isolation from reads. So no ooming ingesters, no compute overheads. We can already see our reliabilities even better. And we are not compromising on the high availability. And new Loki now can partition by volume, and capacity planning becomes quite predictable instead of being reactive. And Kafka gives us more knobs to play around with the different partitioning models, so we can further optimize how much responsibility we give to the write path or the read path to put which data together. We are still cost efficient, so data is written once. Imagine when you replicate data, you have to pay the compute memory and network of replicating that data in running components. And then in the object storage with the mentioned problem of duplicates, you duplicate data and pay for it. And then in the read path, you again have to pay for the compute to deduplicate again. So even after the new costs of running Kafka, when we remove the cost of deduplication, or duplicates and deduplication together, we can see up to 30% of reduction in our largest clusters. This is significant, transformative for large-scale deployments. So there's more we can list here. Kafka enables us to experiment and iterate faster by adding more topics, exploring different processing models, partitioning models. So the new streaming layer is the foundation of the new flexible data pipeline. Thank you for walking with me the new right path, but this is only the halfway. We just discussed how the data gets in. Now I want to hand it over to Ben Clive and Trevor Whitney to tell you all about how the data gets out.
Great, thank you, Poyzan. So now you've heard all about our write path. Trevor and I would like to talk to you about the query path. In particular, the queries that Loki processes today that are inefficient and how we improve them using a new query engine and storage format. So we've seen an increase over the last few years of users looking for more business insights from their logs. What are business insights? Well, it's looking for more information related to your business from your logs rather than related to your systems. You can see a simplified example here of a question which might be asked of how many failures did a user experience? And you can see the LogQL metrics query that would get you an answer to that question. These queries today are expensive for Loki to execute, but we have improved them. We'll dig into exactly how in a second. But first, let's look at the improvements we've made. So we have 20 times less data scanned and 10 times faster query execution for these kinds of business queries. This is a really big achievement for Loki, and I also want to say that it's just the beginning. We're still working on this area, we're still doing research, and these numbers should improve over time. First, let's dig into each of these different pieces and see how we improve them, starting with the data reduction. So there are a lot of factors that go into this, but we'll just look at the main one, which is challenges with Loki's current storage format. Loki today stores its log data in a format called chunks. We can see that up to 97% of chunks are storing log lines. That leaves just 3% of the data that we store being things that are not log lines, the timestamps, and any structured metadata you send us. This is the heart of the storage challenge for Loki, because today it will download and process all of this data regardless of whether it's needed or not. So that domination of the log lines within the chunks means that queries can't easily target a subset of the data that we have. A typical chunk contains around 8 megabytes of uncompressed data, and that leaves around 200 to 300 kilobytes of non-log data, so the timestamps and the structured metadata. Even if we could pull all of that data into one place and read it out, we still make a lot of requests from a lot of small files, and that's not very efficient. Unfortunately, chunks are a row-based format as well, which means this data is interspersed with the log lines, so we can't even do that. Based on all of those factors, we decided that Loki would perform better if it had fewer, larger files that could store the timestamps and the metadata separately in contiguous blocks that could be downloaded and processed independently. So that's exactly what we did, and they're all features of columnar storage. So I want to introduce DataObjects, a new columnar storage format for Loki built specifically for logs. We'll go into a bit more detail in what makes the DataObjects good for Loki, but first I'm going to pass over to Trevor, who's going to talk to you about the query execution times.
Thanks, Ben. So I want to talk about the other performance improvement Ben mentioned, which is 10 times faster query execution. And we're going to tell you how we achieve that with the new query engine. But before we do that, let's refresh our memories on how the current query engine works. So before I dive into this, Who in the audience has struggled with cardinality in Loki before? I have. So definitely some of you. Cardinality has always plagued us because it impacts density. And that in turn impacts the amount of data that Loki needs to scan to answer a query. Today, reads come into the query front end. They get split by time and sharded, sent to the scheduler where they're picked up by a querier. These queriers operate on chunks, and these chunks can have significantly different density. And what I mean there is how many of the log lines in that chunk are relevant to the query that you are running. Often the log lines aren't pertinent to the query, but Loki still needs to read that log line in many cases to determine that. And so the size of the log line dominates the performance of the query. As we have seen in the evolution of logging, as Poyzan mentioned in the keynote, we are seeing an increasing number of dimensions in logs of today. And so now the query path must scale up to keep up with those increasing dimensions. You do not need to read this slide. It is a lot of words. I understand that, but I did want to include this because this comes straight out of the 2018 design document that the Loki was originally designed around, the original design document for Loki. And I wanted to talk about the original design for Loki because I wanted to highlight that despite these challenges of the log line dominating the query and the current architecture, Loki is still an efficient, performant, and scalable database. We have scaled it to what some might say using an embarrassing degree of parallelism to scale to the loads that we need to be able to handle with our open source and our cloud customers. And in this paragraph, as you can see, where there's a discussion about storing structured event-based data, about answering analytical type queries, and then specifically concluded with this is not something we are targeting with the system. So I bring this up to highlight that the query engine of today is not broken, but the query engine of tomorrow will unlock so many new use cases. And so that's going to open my conversation of the new query engine. The Loki that we have today, the query engine of today, is designed to operate at the level of the log line. The new query engine is going to be able to operate below the log line. This means its performance will no longer be tied directly to the size of that log line. It's going to allow us to answer more questions at a bigger scale. This is all possible thanks to data objects and the way that they're structured and allowing Loki to do less work. So here's the new query engine. Looks a lot like the old one, but there are some significant differences here, so let's talk about those. So when a query comes in, the first thing that we do is we write a comprehensive query plan. This includes a logical plan, a physical plan of how to actually read that data, and a clear execution strategy. What this allows us to do is pull out optimizations and then push them as far down the stack to exactly where they can be the most useful. The plan is split into fine-grained tasks for scheduling with these optimizations pushed down into them. This allows the data object scan work to scale out elastically and read less data during scans. Finally, this work is distributed via a tenant-aware queue, so the system is protected from any noisy neighbor queries that another tenant might be running. The key optimization to this whole new query engine was to read less data. By detecting predicates early, we can push them exactly where they're needed, and that allows us to filter early and only process the dimensions needed for that specific query. I may use the word dimension a few times, I might have already, so just real quickly, what I mean there is just any queryable property of a log. So in this example, service, response, user, those are all the queryable properties here and dimensions. Okay, so how do we do this? Let's walk through the new query engine using this query as an example. And we're going to show off how we achieve that 20x reduction in data and those 10x faster query executions. So the query comes in. The first thing we did, as I mentioned, is plan. So today with chunks, you often have to read the whole log line to answer any query about it. And log lines can be broken up into many different parts. So for example, in this log line, I've kind of grayed out the log line because it's not as important, and I'm highlighted the stream labels associated with the log line, as well as some key value pairs that were included as structured metadata with this log line. With data objects, we store these different dimensions in their own columns. This allows us to selectively read those columns. And at the planning stage is where we sort of figure out the pieces that are going to be needed, and so we can push them down into the plan where they're needed. With chunks, the philosophy was read everything and then filter. In the new query engine, we filter early, scan selectively, and we only process the dimensions needed for that specific query, which of course results in faster queries over less data.
If we take a look at the whole log line, we can actually see there's more properties, more than just the stream labels and the structured metadata that Trevor already mentioned. We also have the timestamp, the log message, and detected fields. Each of those are a candidate to be pulled into a column in storage in order to speed up these queries. But not all of these dimensions actually get pulled into storage. Here you can see the same data that we just had, but pulled into a columnar format. You can see the timestamp, the log message, and the response and user structured metadata is all there. The notable exception is the detected fields. We don't currently pull those into columns in storage, but we still process them as normal on the query path. We'll talk a bit more about that later, about why we didn't do that. So let's work through this data in a small example and see how do we execute a log query over columnar data, and how is that better? There's two main steps we would take for a query like this. The first one is to scan the response column for the string failure, and then for any matches, we will read out the relevant columns for that row. By not reading the other columns for rows which don't match that response filter, we save ourselves bytes that we need to process and ultimately saving on query time. But can we do any better? We can see that for a metric query, we don't need to read the other columns at all for any matching rows. We can simply filter the response column for the failure as before, but then we don't need to read out the log message, the timestamp, and the user. We simply count the number of rows that matched. As we've seen previously, a significant portion of our data is in the log message. So if we don't have to read that, we can save ourselves a huge amount of bytes, a huge amount of compute, and ultimately a huge amount of query time. Let's drop down now to the storage layer itself and talk a bit about the data objects. Loki obviously is a object storage friendly database, so our data objects are always also object storage friendly. Some of the features we have that work well here are front-loaded metadata. That means that all of the metadata about what's in a data object is at the front of the file. So that's the columns, the pages, the byte ranges we have, or any statistics that we need. And that means we can quickly read and discard a whole object's worth of data very quickly if it doesn't contain any data that we need. We also support multi-tenancy as a first-class citizen. That means that if you're running Loki in a cloud environment with many tenants against a shared bucket, you won't have any concerns with sharing your data between people. Finally, accessing data in a data object is low latency by design. You can read any range of bytes in just 2 round trips to object storage. The first one will read the front-loaded metadata, decide what byte ranges it needs, and then we fetch all the bytes that we need in another trip in parallel. Beyond those object storage features, data objects have a lot of features that are common to many columnar file formats, but actually they're also perfect for logs. The first one are various encoding and compression strategies available on every column. This is particularly good in logs because we see that a lot of metadata keys have very similar values. You can think about the Kubernetes pod name, for example. They all tend to start with the same few characters, which means we get very good compression. We've seen up to 1,000x column compression here. We also have full support for sparse columns. Again, this is very important for logs because not every log line will have the same key defined on it, which means a lot of log lines won't have a value for a particular column. So by supporting sparse columns via presence bitmaps, we can scan data very quickly and decide whether we need to read any data from those columns. Finally, we have paged access to the data, which means we can read a small amount of data at a time and process it efficiently. It also means we can cap the maximum amount of memory we need to use to do a read. But on the flip side, we can allocate more memory, read more pages at once, and get even faster queries based on the amount of memory we have available. This level of control means that we can avoid out-of-memory events in a lot of cases, and it makes it much easier to size our tasks to our queryers that can run the actual queries. Right, so that brings us to the bottom of our query execution stack. I'll hand you back to Trevor to go back up and put it all together.
Great, thanks, Ben. So yeah, this is just putting all these pieces back together as we go back up the stack here. So as Ben just described, we can selectively scan data. So that for this query, we only need to know the user and the response column. So that's in blue. We can reduce the amount of data that we read when scanning that data using those predicate pushdowns, those logical bits that we detected in the query plan. We push down to the scan nodes. That represents these are represented by these gray lines, where we only need to actually pull the rows where the response is failure. And then finally, we do all this work in batches using the pages that Ben mentioned. So you can see here the vectorized execution in red. We can do this sort of one piece of data at a time. Going back up one level, and here you can see the query at the top. I have an admission, Ben, this query is wrong. So someone who's been working on Loki for 5 years, I screwed up a LogQL query, so the next time you screw one up, just remember that. But we're missing the by user aggregation here, so imagine that that's there. And here, we're in the aggregation phase. We've reduced the data that we need even more. We already evaluated the response equals failed predicate when scanning data. So here we actually only need the user column to aggregate over the user. This targeted I/O reduces memory overhead as well as unnecessary computation cycles. This results in faster queries for the users and more controllable load for operators. So that's DataObjects and the new query engine, which greatly improves the experience of running Loki at scale. And you may be thinking to yourself, wow, they thought about everything. They solved every problem. But there are a few still out there. So I'd like to talk about, or we'd like to talk about a few of those. The first one being detected fields. So as Ben mentioned earlier, there is often structure in the logline itself. And historically, Loki has always had to parse this structure at query time. So for example, right, the duration and method here. In the new query engine, I'm very excited to announce, we still parse this information at query time, but we hope to stop doing that soon. If we're able to pre-parse this data, put it into columns, we're going to get all of those columnar advantages we get from the other metadata. This would also greatly improve things like the detected fields endpoint. Anyone in the room use log drill down before? Love logs drill down. Awesome. Excited to hear that. It relies on this endpoint, which is right now a best effort sampling of the fields in your log lines. Pre-parsing those would allow that endpoint to perform and be exhaustive, comprehensive, and perform at scale. But part of the reason we haven't done this yet is because it's going to exacerbate another problem we have, which is the problem of ambiguity. So here we have a few different statements you might see in a LogQL query. And before I go into this section, let me first say LogQL is great. I use it every day to find the exact logs that I need. So we have no plans to add complication to that language. But LogQL was built during the specialized logging services stage that Poyzan mentioned in the keynote. And it was not built for this expansion of dimensions that we're seeing in logs today. As a result, LogQL has no way to allow the user to specify specific types of metadata, like where is this field. Oftentimes, the query engine can determine it, and that's great. We can push those optimizations down to our scanning nodes. But when we can't determine it, we have to read any possible column that it could be referencing, and that increases the amount of work we need to do. So we look forward to solving this and further improving the performance of analytical queries. So stay tuned for improvements to that space.
Yeah, another area we're still working on is the log ingestion and defining an optimal read layout for the log data. One of the big things we wanted to solve with data objects was avoiding a lot of small reads from a lot of objects. Unfortunately, if you're not careful, we still have that problem in data objects. And that kind of starts naturally at ingestion time. We need to spread out the incoming logs into many different machines in order to handle the incoming load. That means we get a lot of different data objects of a fixed size to spread out the data. However, when we want to query that data, the query engine actually prefers fewer files that are larger and have more relevant data in each one. We do want to figure out how to put those together, but at the moment, they're not really working together. They're at odds with each other. To make this problem worse, all the users of Loki are different. You can imagine different tenants have very different data, but also different teams within the same company will query their logs differently. They might have a different key that they use a lot. Maybe they'll search by a different service. And all those things mean that there is no one optimal layout, which is why this is still an ongoing research area. But we are making progress here, and we hope to get better at it, and it will improve over time. OK, so that brings us to the end of the new query engine and storage section. Loki was built to search your logs, but the next version of Loki that we're bringing today is built to analyze them. We've implemented a new query engine and a new storage format to do that, bringing sublinear query times as your dataset grows. All of these will bring more insights from your logs, more queries, and more scale. But there is still one type of query that Loki struggles with, and that is the needle in the haystack we mentioned already. Now, luckily, we have Jason here who's going to talk to us about needle in the haystack and the advances that he's bringing to Loki next.
Good job. Thank you. Thank you, Ben and Trevor. I'm Jason Nochlin. I recently joined Grafana a few months ago, which I'll talk more about in a second. And I'm excited to talk about how we're bringing needle in the haystack query acceleration to Loki. Now, traditionally adding indexes to petabyte-scale log storage required picking between two bad trade-offs. Either you go with the low-cost, easy-to-operate solutions like Loki, but that puts a lot more work on the end users that are making the queries in order to have efficient queries. And so you end up with situations like you're trying to debug an incident at 2 a.m. and you can't remember the right label selectors to use to actually find the request UUID that you need to solve the incident. On the other side, there are solutions out there that offer full indexing, but that comes with a much higher cost, which leads to stress for the person paying the bills. And not only was this situation making our users sad, this was also holding Loki back from becoming the product that Grafana wanted it to be. There's really 3 requirements on this. We can boil it down to 3 requirements on this problem. We want to offer indexing that brings low cost overhead, high precision, and is object storage native. And that has not existed before. But there have been some attempts to solve this. Who knows what this is? Bloom filter, that's right, a probabilistic data structure. And this is what got me interested in this story. So I've spent a lot of time with Bloom filters. At a previous startup, I used Bloom filters and some state-of-the-art variations of them to bring a novel approach to change data capture for database replication. So when I learned about the observability challenges and how people were trying to use Bloom filters to build data skipping indexes over logs, that immediately got my attention and nerd sniped me into this problem space. Now, Bloom filters are a very clever solution, and they have a lot of power, but they have some fundamental limitations that show up when you try to bring them to scale. So based on my prior experience, it was clear to me that they were not the right foundation to use to solve this problem. And that really came down to these three things. Bloom filters are typically thought of as a compact data structure, but at this scale, you ended up having indexes that were nearly the size of the original data set, so they had high storage overhead. They are expensive to query. The random nature and the hash function computations associated with Bloom filters can lead to significant CPU usage, poor cache locality, and then the typical architectures for this type of skipping index will build a Bloom filter per some section of the data. So you end up with a number of Bloom filters to search that's proportional to the size of your data, which means higher query latency with larger amounts of data. So very expensive to query. And on a related point, the random nature makes them not suited for object storage. The poor cache locality results in an inability to read them directly out of object storage with things like efficient remote reads. And typically, to bridge that gap, you need to put in more expensive infrastructure in front of object storage to serve Bloom filters efficiently. And that's where Logline entered the story. So Logline was a company I founded around 2 years ago, and we ended up coming up with a novel solution to this problem. And Grafana got very interested in that solution, and in December, I joined through the acquisition of Logline to bring fast needle-in-the-haystack searching to Loki, and while maintaining the low-cost profile that everyone has been accustomed to. So we're introducing a new index to accelerate needle-in-the-haystack queries to Loki. The Logline technology is powering this and was a natural fit for Loki's architecture, primarily around being written in Go with both of them helped, but on a operational basis, the new indexes are completely decoupled from the Loki write path, so there's no operational coupling. That's both great for keeping Loki easy to operate and also allows us to organize data in the indexes in a way that's best for searching and keep data organized in the primary query engine in a way that's best for all of its operations. So that gave us the great way to create these indexes. It's object storage native. So the Loki builds these index files and then uploads them to object storage. And at query time, we do efficient efficient range reads directly into the index files without needing any additional infrastructure. And we've put a lot of effort into tuning these indexes to be highly precise for needle-in-the-haystack type searches. So really focusing in on what information we need in the index to find UUIDs, to find IP addresses, to find any other unique types of identifiers, and clearing out redundant information like timestamps that appear on every log line that typically clutter indexes. But by removing them, we can keep the index much smaller while maintaining the precision. There's also some tricks to keep these indexes enabling very fast search while keeping the cost low. So we do not use Bloom filters for this, but we've used some custom approximate probabilistic data structures based on bitmaps and some custom hash maps associated with that. And the result is we have an index that has less than 20% storage overhead. And also the structure of them lends itself to predictable lookup costs. So the cost to query the index in terms of resources to read them from object storage is proportional to the size of the query and time. So longer queries will have a higher lookup cost, but it is not dependent on the size of the data. So no matter if it's terabytes or petabytes, we'll keep low latency, low cost on the query path to add the search capabilities. This is how it'll be integrated in Loki on the query flow. So we have a function that detects potentially expensive queries because there is some latency associated with the index. So we want to make sure we're only invoking it in the cases where it helps. When we identify one of those large queries, we parse it and probe the index with the search terms. And then that returns us a list of likely matches of locations in the data where the query result may be. And then we pass the likely matches off to the new Columnar storage engine and have efficient processing to find those log lines within the identified regions. And does it work? We seem to be getting great results in the initial dev environment. So this was an example query that I ran of looking for a UUID with no label filters. We had, with Loki today, you would look at, the estimated data volume was 3.5 terabytes. And when I actually executed this query, I got a client timeout. So this hit the resource limits in this environment, which I believe was like something like 60 seconds. With the new indexing, we were able to filter the 3.5 terabytes down to only 8 gigabytes of logs we needed to scan to find this UUID and return the result of finding that exact needle in a few seconds. So as I said, the technology was acquired in pretty early form, so we've been focused on the effort to integrate it into Loki and make sure that it's working at scale. The next step is we're going to bring this into Grafana Cloud so we can verify the index to ensure correctness and also tune all of the parameters to get it working as best as possible for the various use cases the various needle-in-the-haystack use cases that customers are using. And then later this year, early next year, we will bring this into a OSS public target for the community. And yeah, that's in addition to this new indexing, there's some other great things coming to Loki open source. So I'll bring Trevor back up to talk about that.
Hello again. So as Jason just mentioned, everything that we've talked about today is either already in the Loki repo, the open source repo, or planned to be there as soon as that we are able. And so I'm really excited for all these features to land in open source. One thing you may be wondering, how many people in the audience run their own Loki stack? Anyone here? That's a lot. That's awesome. I love that. And so how many of you are now wondering, do I need Kafka? So let's talk about that. As Poyzan mentioned, we are committed to the monolithic mode, also known as the single binary installation. So if you are running a small instance of Loki that can fit on a single machine, you will not need Kafka, and that's our commitment to you. If you are running a distributed system, then you will need Kafka, because that is going to be our new orchestration mechanism for a distributed system. And the trade-off there is, yes, maybe slightly more complication to your install, but you will be able to handle much larger scale. And as Poyzan mentioned, we're seeing 30% reductions in costs at equivalent scale. So I think the trade-off will be worthwhile. We have been running this new architecture ourselves in both our internal operations environment as well as a few production cells. And as a result, we have developed some tools to safely migrate, to safely run this system. And those tools are also available in the open source repository today. What this looks like, how we're running it today, is writing into Kafka and then having two consumers out of Kafka. So we have a consumer that writes chunks. Looks a lot like the ingesters of today, but it reads from Kafka instead. And then we have the new consumer that writes data objects. In front of these two different storage types, we have two different query engines. So there's the queryers of today, which read from chunks, and then there's the new query engine that I just presented on. This allows you, by running both query engine, this allows you to continue to query any chunks that your system might already have. And you can run the systems in parallel until those chunks sort of age out of their retention period, and then you could switch to just using the data objects. In order to allow you to run both query engines, we have a new component in the open source repo called the query T. And it is configurable with a few different routing modes. So you can configure it to always favor the chunks response. You can configure it to always favor the new response, or you can have the responses race. And you can return whichever one is faster. And that component has all sorts of metrics, so you can monitor the sort of correctness between the two and make sure that the new engine is producing results similar to how the old engine worked. And that's it for the new Loki architecture. We are going to bring everyone back up on stage for questions. But real quickly before we do, just want to let everyone know that all four of us will be at the Ask the Experts booth directly following this talk. So if you have questions that don't get answered, please come find us. There is on play.grafana, there is a Loki data source called Loki DataObjects that is using the new architecture. This is still actively in development. Not all queries are going to be faster, but some will. So find the ones, especially those analytical ones, that are performing better, and continue to look at that data source and watch as we continue to develop this. That's available in the demo, the self-serve demo booths that are all around. And finally, there's a Loki architecture banner. I think I saw the one over there. I don't know if there's more than one, but go take a picture and then come find us at the Ask the Experts booth if you have any questions. So with that, come on back up, everyone.
Trevor and the team, everybody, please give it up for them. Thank you so much. Excellent.
Yeah.